Hello everyone, this is Mishra from section A3. My roll number is A3B349 and I'm here to explain the Stern-Gerlach experiment as teacher's assessment 2 for the subject Introduction to Quantum Computing. So let's get into it. In 1922, two physicists, Otto Stern and Walter Gerlach, conducted an experiment that would change our understanding of the atomic world forever. They wanted to test the bold idea of the emerging field of quantum mechanics, spatial quantization. The idea that orientation of angular momentum in atoms would only take certain discrete directions. This experiment delivered the first ever experimental proof of the fascinating degree of freedom of an electron spin. They were the first to demonstrate that the spin of an electron is quantized or separated in up and down direction. It was a sensational achievement at that time. Before we dive into the surprising results of this experiment, let's take a moment to understand its key components. What made this setup so special? Why did they choose silver atoms? Why was the magnet designed in such a unique way? And what kind of magnetic field did they produce? Most importantly, how did the results of this experiment completely shock the physicists and challenge everything they thought they knew about the atomic world? The key component of this Stern-Gerlach experiment was the oven, where the solid silver was heated to a temperature of about 1000 degrees Celsius, causing the silver atoms to vaporize and escape through a narrow slit. So the question arises, why only the silver atoms were used and not any other atom? So the first answer to this question is the silver atoms are easy to vaporize. Second is that silver has exactly one unpaired electron, which is easy to measure the spin. So as you can see here is the electronic configuration of a silver atom. As you can see the configuration, it's 1s2, 2s2, 2p6, 3s2, 3p4, 3d10, 4s2, 4p6, 4d1 and 5s1. So this one electron is the only deciding factor of all the magnetic properties of a silver atom. So as it's only one electron, we just have one spin here. So it's easy to measure the magnetic properties and this outcome spin here. Another reason of using silver atoms is because of its neutral nature. We know that silver atoms only react to the magnetic field and not the electric field. So any complicating factor here will be cancelled out as it's neutral in nature. Next reason is that silver has high boiling point, so it makes it easy to create a narrow straight atomic beam. Another thing to observe here is the special shape of the magnets. You see one of the magnets is sharp on the edge and other one has a concave surface. So this setup is especially made for creating an inhomogeneous magnetic field. Here is the catch. You see a uniform magnetic field would not separate the atoms. Hence, special shaped magnets were used to create a strong, non-uniform magnetic field, which produces the force necessary to split the atomic beam according to their spin. Next, we will examine the experimental setup of the Stern-Gerlach experiment, focusing exclusively on the apparatus and its functions. The experiment begins with an atomic beam source. As I have discussed earlier, silver atoms were used due to their single unpaired electron, which provides a well-defined magnetic moment. A small oven is heated to produce a vapor of neutral silver atoms. As the atoms escape the oven, they pass through a narrow opening, forming the initial beam. Second is the beam culmination, which are the slits. To ensure the beam is well defined, one or more slits are placed downstream from the oven. These apertures restrict the trajectories of the atom, allowing only traveling approximately parallel to beam axis to continue. This slit is essential for producing a narrow, uniform beam that can be specially resolved at the detector. Next is the non-uniform magnetic field. At the core of the apparatus is a region containing a non-uniform magnetic field. The field is generated by two specially shaped magnet poles, typically consistent of one of a flat pole and one sharply curved or tapered pole. This geometry creates a significant magnetic field gradient commonly oriented vertically. As the slit beam passes through this region, each atom experiences a force proportional to the gradient of the field and the orientation of its magnetic moment. Now let's take a look at the actual working of this experiment. Today we'll be learning about the Stern-Gerlach experiment. It was introduced by two physicists in 1992, Stern and Gerlach. So this is the setup for the Stern-Gerlach experiment. Here you can see a silver block which is heated to 1000 degrees of temperature. It will start dissipating the atoms. You can see a narrow beam of electron. It will pass through two slits. You can see there are specially shaped magnets. This has a huge importance because this special triangular magnet and this block rectangular magnet, they will produce a non-uniform magnetic field. So this electron beam will pass through this non-uniform magnetic field, and it is observed that there are 2 points where the electron beams are concentrated. One is having a spin plus and second one is having a spin minus. So this is what should have happened classically. So if we use a uniform magnetic field, the electrons passing through two magnets which having the magnetic field be downwards. So it should the concentration of electron beam should be out of the page and at one place only. So this should have been the electron cloud. These are all the electrons, but in Stern-Gerlach experiment we see that this is the output. You can see two curves where half the electrons are in upspin and other half are in the downspin. Let us once again examine the results of the Stern-Gerlach experiment. Classical physics predicted that the beam of atoms would spread out in a smooth, continuous band on the detector. Some atoms would be deflected slightly upwards, some strongly upwards, some slightly downwards, and so on, forming one wide blur or a smear on the screen. But the actual result was completely different. The beam did not form a blur, not a smear. Instead, it split into exactly two sharp spots with nothing in between. It was either up or down. This showed that the atom's magnetic moments could only take two specific values, not any direction they wanted. So we now can call these two outcomes spin up and spin down. These results also laid the groundwork for understanding the role of spin in the structure of atoms. Spin is now known to be a key factor in the arrangement of electrons in an atom, the behavior of atoms in magnetic fields, and in determining the chemical and physical properties of matter. Without this experimental evidence, the modern framework of quantum mechanics would have not been possible. This experiment, therefore, was a crucial step in bridging the gap between theoretical predictions and experimental verification in physics. In conclusion, the Stern-Gerlach experiment provided the first direct evidence of quantum behavior in atoms, confirming that atomic properties like angular momentum are quantized. At the time, this was a revolutionary discovery, challenging the classical view of physics and opening the door to a completely new understanding of the microscopic world. The experiment shaped modern science in profound ways. It helped physicists develop a more complete and accurate model of the atom and contributed to the foundations of quantum mechanics. Furthermore, it has influenced a wide range of technologies that we rely on today. By demonstrating that microscopic particles have intrinsic properties with discrete values, the Stern-Gerlach experiment has fundamentally shaped the way scientists study and manipulate atomic and subatomic systems. It continues to guide research in physics, chemistry, and material science, highlighting the essence differences between classical and quantum descriptions of nature. Overall, this experiment remains a cornerstone of physics in quantum physics. It was not only confirmed theoretical predictions, but also a clear experiment demonstration of the quantum world, showing how careful observation and experimentation can reveal the true nature of matter at the smallest scales. The Stern Gerlach experiment, therefore, is not just a historical achievement, but a continuing source of insight into the behavior of quantum world, shaping both science and technology in the modern era. Thank you.